Dear students, in this class, we discuss about secure hash algorithm. And in this also, today we discuss about Sha-512 algorithm. What is this secure hash algorithm? You know already. In the previous classes, we discussed about message authentication. So what is this authentication? It is the procedure to verify user identity identity and not only that identity, integrity of the message. So for providing this authentication, which is used to verify the mainly the user identity, we are having some message authenticators or message authentication functions which are classified like one is message encryption, and the second one is message authentication code, which is nothing but MAC code. It is of fixed length, and this message authentication code will be generated with the help of that some function, so which takes the plain text M and the key K as input, and it generates that message authentication code. Then the third one, the message authenticator is hash code. Hash code. So to generate these hash code, so we can also call it as message digest. To generate this hash code, we use some hash function which takes only the plain text as the input and is generating that hash code of fixed size. Hash code of fixed size. So this hash code, how we can generate this hash code? Now we will observe that how we can generate hash code, the third point, with the help of this SHA algorithm. Actually, this SHA algorithm is having different versions, different versions. So you observe here, these versions are, I'm listing the versions here, and plain text, plain text maximum size of that plain text, and then block size, block size. Then here we use few words, word size, word size, and message digest are hash code size, hash code size, message digest or hash code size. What are the versions here? Like these versions we are getting based on the size of the hash code that algorithm is generating. If it is 160-bit hash code, this is in terms of bits we are saying. So if it is 160-bit hash code, so this is nothing but SHA-1 algorithm. So if it is 224-bit hash code, it is SHA-224, and then it is, if it is 256-bit hash code, then we call it as SHA-256. Then we are having SHA-384, means it is generating a hash code of 384 bits. So that is SHA-384. Now our topic is SHA-512. So which is nothing but the hash code of size 512 bits. So that is nothing but SHA-512. So what is the plain text message size, maximum size for these algorithms? Here, the plain text maximum size for the SHA-1 algorithm is less than 2 power 64 bits. 2 power 64. It is not 64 bits, it is 2 power 64. You know, if it is 2 power 5, we will get 32 bits. If it is 2 power 10, it is 1024 bits. So 2 power 64 means, so some big number, you will get more number of bits here. So in SHA-224 algorithm also, it maximum plain text size, it is 2 power 64 bits. So 2 power 64 for 256 also. For 384, it is 2 power 384. Then this SHA-512, sorry, sorry, this one is 2 power, not 384, this is 2 power 128 bits. And for SHA-512 also, the maximum plain text is 2 power 128 bits. So you see the last two versions actually, what is the maximum plain text size? Is 2 power 128 bits. So that is the size of the plain text we are taking. The size of the plain text may be of any size, any number of bits, but if you want to apply that algorithm, so you need some blocks. You need to divide the plain text into blocks. Here, the SHA-512 algorithm, process the plain text in terms of blocks. SHA-512 algorithm process the plain text in terms of blocks. So what is the block size here? Each block each block is of size 1024 bits. Is of size 1024 bits if it is SHA-512 algorithm. Block size is 1024 bits. And for this also it is 1024 bits. And for this it is 512 bits. Block size is 512. 512. So like this. So then, in the previous encryption algorithms, along with the block size, generally we use some keys like that. Here, in every round operation of these SHA algorithms, we use some words. So we call them as keywords. So for these first three versions, the word size is of 32 bits. All these are in terms of bits only. So this is also of 32 bits. Sorry, this is 32 bits, 32 bits, and this is 64 bits. The last two are of 64 bits. Okay. Now we start this Sha-512. Sha-512 means here you are using some hash function which will be applied on the plain text, and it is producing a hash code. H is representing hash code or message digest. Hash code or message digest, which is of size whatever may be the plain text. What is the hash code size here? If it is SHA-512, that output of the algorithm is giving a hash code or message digest of 512 bits. It is of 512 bits. Okay. So now, what are the main steps that we need to concentrate here? Yes. First, you observed the plain text, maximum plain text size, plain text. Generally, we represent with M. What is the size? It is less than 2 power 128 bits, like that we are saying, very, very big number. So now, if the plain text is of size, big size, okay, or it may be less than 1024 bits, like that also, then what we will do here, we process the plain text, process the plain text in terms of blocks. So in the previous unit, every encryption algorithm maximum that what we discussed like DES, AES, Blowfish, all those are block ciphers. So they will take one block of plain text and they will encrypt. Same like that here also to generate a hash code, the plain text is processed in terms of blocks. So, if you are talking about the blocks, what is the block size? So, already we observed the block size is 1024 bits. Block size is 1024 bits. So then after this, in the algorithm design, in the previous algorithms also, what we observed, so any rounds will be there in this algorithm? Yes. So here we are having one function with the name round function, so which is represented with capital F. So it contains some number of rounds. So how many rounds will be there? Here this each block of 1024 bits will undergo for some round function. In this function, so we are having totally 80 rounds. 80 rounds. So we represent those rounds like round 0, round 1, like round 79. So 80 rounds will be there. So next, here in this algorithm, in every round, 80 rounds we are saying now, in every round, we use some words. Those words are called as few words. Those words are called as few words. So it is represented generally with W. W. So for every round, we use one word. So how many words will be there? 80 words, which are represented like W0, W1, W2 up to W79. Okay. Here, each word is of 64 bits. Each word is of 64 bits, and these words are represented in hexadecimal form. These words are represented in hexadecimal form. Okay, so how to generate these words? These words are generated from the plain text. These words are generated using that plain text, mainly for every block that you are using. So which is of 1024 bits. Using this, so the plain text is processed in terms of blocks like that we are specifying here. So each block, which is of size 1024 bits, will produce 80 keywords. 80 keywords. How these words will be produced or how to generate these words, we will observe. Okay. So first, this is very basic thing. What we will use in this algorithm like that I am discussing first. Then here, along with the words, in every round, out of 80 rounds, in every round, we use some additive constants. Additive constants. Like these are like round constants in our previous algorithms. Round constants, like round constants, here we are using additive constants. Mainly here we are using one operator, that is addition modulo 2 power 64 operator, which is represented like this. This is addition modulo 2 power 64. So you know what is addition modulo operation? So for example, I am taking here 2 addition modulo 3, 5. What is this? It is nothing but the remainder when 2 plus 5 is divided by 3. So what is the remainder? 2 plus 5 means 7. So here we are performing integer division with 3. So it will go for 2 times. So the remainder is 1. So this is addition modulo 3. But what is this value here? Addition modulo 2 power 64, the big number. Okay. So just I am giving the idea about what is this addition modulo operation here. Next, you come to this round constants. So here we are using some additive constants. Because of this word, I am giving this. So anyway, that is useful. So additive constants. So for every round, we use one additive constant, which is represented like K naught, K1, up to K79. So how to generate these round constants, we will observe, or these additive constants we observe. So next, another point that we need to discuss before starting this procedure is here we use buffers. Generally, buffers are used to for storage purpose that you know. So why we use these buffers in this algorithm? So we are talking like here in this algorithm, we are having totally 80 rounds like that. So while performing different round operations to store intermediate results, Mainly, why we need these buffers? These buffers are used to store intermediate results, and then after final round, we need to store the result, to store the result. What is this result here? That is nothing but hash code. What is that? That is nothing but hash code. So that is the message digest. Okay. So here mainly these buffers we are using to store intermediate results between every round operations. So two rounds, between two rounds, if you want to store the results, intermediate results, we need those buffers. Then finally, to store the result also, what is the result? It is nothing but hash code. To store that result also, we are using these buffers. Okay. So then how many buffers are required here? Number of buffers. So the number of buffers is nothing but, because the hash code is of 512 bits, so the number of buffers required is given by, here each buffer is of size 64 bits. So each buffer is of 64 bits. So how many buffers are required in that case? Total hash code size is 512. So to store these 512 bits, so how many buffers are required? Because each buffer is of size 64 bits, we need only 8 buffers. So the number of buffers required here, it is 8 buffers. Okay. So these are important points here to start our algorithm. Okay. So now you observe here the procedure. I'm writing like steps here. So what are the steps that we have mainly? So the first step is append padding bits. Append padding bits, and another one, it is append length of original plain text. Append length of plain text. First, we discuss about these two steps, then we go for the next steps. Because we wrote like the plain text is processed in terms of blocks. Okay, so how we are representing the plain text? Plain text we are representing with M. So this is the original plain text. So here we are having the plain text which is represented with M. So the maximum size of the plain text like that. So it contains some number of bits. For this, what we have to append, we need to append some padding bits. So padding bits. What are these padding bits? So these are nothing but 1 followed by zeros. So for the message, for the plain text, how many padding bits? What are the padding bits here? Padding bits are 1 followed by some set of zeros. So like this, how many padding bits we need to append for the original plain text? So this original plain text bits M contains some number of bits. If you add these padding bits, the number of these two must be the number of these two must be congruent to 896 mod 1024. But if I say like this, it will be difficult to you. So for that reason, I am giving one simple example here. So how we have to take? So for example, I'm taking only first one block. One block means totally it must consist of 1024 bits. It must consist of 1024 bits. Okay, then. So then if your plain text consists of, that is original plain text, M consists of, for example, 800 bits. 800 bits. Then how many padding bits we have to take here? Padding bits. The number of padding bits is 96 bits. So what are those padding bits? First bit is 1. The first bit is 1 and the remaining bits are zeros. Like this, how many bits we have to append after these 800 bits? So your plain text, original plain text M consists of 800 bits. For these 800 bits, we are appending padding bits, padding bits. So these are how many? 96 bits. Why we are considering only 800 plus 96 means 896. The maximum block size that you are taking, it is 1024 bits only, no? So at the end of this, so here I am explaining this plain text block processing, how it will be with the help of only one block, not by taking more number of bits to get the clarity. Okay, so here at the end of this, now totally we are having 896 bits. But to get this 1024 bits, we need one. So this is 896. We need some more bits here. How many bits are required? 128 bits. So after appending padding bits, you are getting the block size which is less than 128 bits for that actual block size, that is of 1024 bits. So in these 128 bits, what we will take? So you observe this second point here, that is append length of plain text. So here we are taking length of the plain text. So what is the original plain text length? 800 bits. Okay, these 800, 800 is the length. That is the length of the plain text. That 800 you need to represent in the 128-bit format. 128-bit format. So these 128 bits, which are representing actual original plain text message length at the end, for these 896 bits, that 128-bit format we have to add, that is append. So if it is only one block, then it will be the case. So if you are having more number of bits, not less than 1024, then what you have to do? So then you have to append those padding bits. So after this plain text, original plain text, you are taking padding bits, no? So these padding bits and this original plain text message together, if you add these two, these total bits, sum of these two must be less than 128 bits for the multiples of 1024, because After adding 128 bits, you are getting the processed plain text. Not that is original plain text. M is only the original plain text. For that, we are appending padding bits and then we are appending the length of the plain text in 128-bit format. So here these two, the length of these two must be less than 128 bits for multiples of 1024 bits. So this is the case. The same we are representing with the help of congruence, congruence operation. Okay. So for theory, you can remember this, but better to understand that in this way. Now we observe how that message is processed and how it will be divided into blocks like that. So what we observed, so first we are taking M, which is nothing but the original plain text message, then padding bits, which are nothing but one followed by the zeros, then message length in 128-bit format. So this is giving length of the message in 128-bit format. This is the original plain text and these are padding bits. So after this processing, what we will have, the total length of this processed message is how many bits? It will be in multiples of 1024. So some n into 1024 bits like this we will have. This n into 1024. So now what is that n represents here? It is representing number of blocks. It is representing number of blocks. After appending operation, so maybe after padding the bits and adding the length, now you can divide this processed plain text into blocks. Here, each block is of 1024 bits. So block 1, first 1024 bits of this process message is the first block, which is represented with M1. So what is this block size? 1024 bits. Same, next 1024 bits. So these are representing next block, which is represented with M2. So M2 is also of size 1024. So like this, we will divide the plain text into blocks where each block is of size 1024 bits. How many blocks are there? N blocks. So the last block is represented with M suffix n. This block is also of 1024 bits size. Okay. Now, as we discussed, each block which is of size 1024 bits will undergo for some round operation. So that round operation will be done using that round function. So we are giving the plain text block as input for round function, and this one is given as input for addition modulo 2 power 64 operation. Okay, and here it produces the output, which is nothing but hash code which is generated for this plain text block M1. Actually, this is H1. To generate this, we use some initial vector also. Initial vector. This will be given as input for this function, round function. It is taking the plain text block and this initial vector also. Okay, this initial vector is of size 512 bits. Okay, so the output of this function is given for this addition modulo 2 power 64 operation, and for this one more operand, it is initial vector, which is of 512 bits. So now here, after these two operations, it is producing the round one hash code. Round one hash code. Next. Next block, which is also of 1024 bits, it will be given as input for the round function f. Sorry, this is f only. And the output of this is given for addition modulo 2 power 64 operation. For these two, we are giving one more input like cipher feedback chaining mode. Here we are giving the previous block hash code as input for these two. This is nothing but H1, hash code 1. This is also H1. These two, the output of this addition modulo 2 power 64 is producing hash code for that block 2. But for this also, we are using first 1024 bits to this H2 directly, not using those 1024 bits of that block 1, but indirectly, because this H1 is generated based on these 1024 bits. So H2 also is using all these plain text bits. Okay. So then this one will be given as input for next round function and that addition modulo 64 operation. Same like that, if we continue, the last block, which is of 1024 bit size, will undergo for that round function, round operations. So after that, we'll apply addition modulo 2 power 64 operation. For this, we will give hn minus 1, that is the previous block hash code. So this hn minus 1 as another input for this hn minus 1. So then the output of this will be the hash code hn. So this one is the final output that you are getting. This is the final output that you are getting. So this is nothing but our hash code, so which is of 512 bits. So this is like a block diagram here to you. So in every block operation here, you are having one round function round function that is taking the plain text block, which is of 1024 bit size as one input, and that initial vector or that hash code of the previous round, that is like hi minus 1, and this hi minus 1 will also given as input for performing addition modulo 2 power 64 operation. So, and for this, another input is output of this round function. Then it is producing hash code hi, hi. So while producing hi, we are using hi minus 1 of the previous block. Okay. So this is just like a block diagram for how the message is processed and how that hash code will be generated like that. So then you are having here initial vector. So you can represent this like H naught because all these are nothing but hash codes, but this is actually not hash code, which is not generated by the algorithm. You are taking this initial vector. So better to represent this one also like H naught. It is of 512 bits. Okay. So here we'll observe third step, that is initialization of buffers. Initialization of buffers. So why we are concentrating now on these buffers means you are taking like that initial vector which is represented like h naught. It is of 512 bits. Okay, this is like initial vector we are saying means, so how many buffers are needed? Already we discussed at this point now. 8 buffers. Here, these 8 buffers generally we represent like A, B, C, D, E, F, Z, and H. Totally 8 buffers. You know, each buffer is of 64-bit size. Each buffer is of 64-bit size. So for this initialization of these buffers initially, that is to write h naught or initial vector, how we take the values in these buffers. So first, for example, to write these initial values for those buffers, you have to consider first 8 prime numbers. So what are first 8 prime numbers that you know? It is starting from 2, 3, 5, 7, 11, 13, 17, 19. So then after having these 8 prime numbers, then how we can write the values of those buffers? So here to write or initialize the first buffer, that is A, here we are using square root of that first prime number, which is nothing but 2. Square root of 2. You know, the square root of 2 is like 1.414 and some value. So this is actually in the decimal form. This is in the decimal number form. But write this decimal part of this square root of 2. This fractional part is there now. These bits you write first in the binary form. After writing those binary bits for the decimal part, from these binary form bits or binary digits, consider only first 64 bits. You consider only first 64 bits and represent those 64 bits in the hexadecimal form. So if you convert these 64 bits into hexadecimal form, so then how many hexadecimal numbers we will get actually? Only 16. 16 fours are. To represent one hexadecimal number, we use four binary digits. Okay, so divide them into four bits, then you will get four hexadecimal numbers. So for A, to initialize A, we are using square root of 2. So represent that square root of 2. Actually, that is in decimal form, but consider or concentrate only the fractional part or the decimal part of this number, not this integer part. Convert that into binary form. So in that binary form, you consider only the first 64 bits and represent those 64 bits in the hexadecimal form. Those hexadecimal numbers you can use for initializing A. Like this, for B, it must be initialized with the square root of 3. You have tried converting that decimal part into binary form, then considering first 64 bits, writing those 64 bits into hexadecimal form. Like this. Finally, for that h, we use that square root of 19. Okay, so this is initialization vector, or how we initialize these buffers. So initial values of these buffers. So what is the use of these buffers? These buffers are used to store intermediary results and to store the output also. So these buffers, first we are initializing with these first 8 prime numbers, okay, in the hexadecimal form. Okay, so your initial vector, how it will be actually like this. 8 buffers. 8 buffers. Each buffer is of 64 bits. So totally this is 512 bits. Initial vector is of 512 bits. So then after this we will observe how we can process the message in 1024 bit blocks. How to process the message. So it is also like a block diagram only to you. So what we will have here. So you observed already. So what you observed in the first diagram, here we are having one round function f, which consists of 80 round operations. For this, we are taking the plain text block. For example, it is mi. Then for this, another input is hash code of the previous block, that is hi minus 1. And the output of this here, it will be given for addition modulo 2 power 64 operation. For this, we are giving again hi minus 1 as another input. So the output of this is hi. Okay. So now you know this round function, 80 round operations will be there like that. We are saying. So now we observe like block diagram of those rounds. Okay. See here, processing the message of size 1024 bits in the rounds. So actually, I'm taking it is like a round zero, round zero in this F, in this F. Okay. So one input of this is, if it is round zero, it will have initial vector is one input and plain text block is another input. So here we are having A, B, C, D, E, F, Z, H. So I'm taking here all these are buffers. So these are for H I minus 1, Hi minus 1 like that, or H naught for example. If it is H naught, these are initial values. A, B, C, D, E, F, G, H contains initial values in the buffers that we discussed in the previous part, that is step 3. Okay. So generally here I am representing these buffers for Hi minus 1. Okay. So this one, round 0. The For this round also, we need one more input which is generated from the message. From this, we are generating keywords. The first keyword that is generated from the message is another input. So then after performing the round operation, we will get the result again. So the output here will be given as input for round 1 like this. We are representing. So here we will have A, B, C, D, E, F, G, H to store the intermediate results like that we are saying. So we are having 8 buffers. So this will continue till that around 79. So here also we'll have those 8 buffers. Okay. So then we need to give another input for every round, that is keyword. So for this round 1, word 1, like this, we'll take for this round 79, keyword which is represented like W79 is another input. So after this round 79, that is round number, actual number is round 80. So this one, all these will be in F only. All these rounds are in F. Okay. So the output of that F will be given as input for addition modulo 2 power 64 operation. Yes. See here, I'm taking all these things as input for addition modulo 2 power 64 operation. Okay. For this addition modulo 64 operation, not only these outputs of this round 80, we need one more input, that is hash code of the previous input, previous block. So please observe here how I am taking that. So this is actually hi minus 1. So for this, from this, actually what we are taking, this one we are giving as another input, is given as another input for this XOR operation. So like second input, along with that round 80 output, we need one more input for that. That is hash code of that previous round. That one we are showing here. Okay. Now, after performing addition modulo 2 power 64 operation, we will get the result, which is nothing but hash code. So these are for hi minus 1. So after performing this operation, these results are stored in again those buffers up to h. So these buffer values are giving hi, hash code hi, hash code. So this is also some idea for you. It is giving some idea for you. So about this round function f, totally 80 rounds are there starting from 0 to 79, and between every two rounds, what will happen and how we will get these 80 words from the message block. This is message block. So how to get those 80 words, that is also important. So another point here, for every round, we said we discussed one point here actually. We use additive constants like k naught, k1 up to k79. Don't forget to add these additive constants, round constants for every round. So this is again an idea about how the message is processed like that. Okay, so here we are using these additive constants or round constants. Now, what are those constants? K0, K1, K2 up to K79. Totally 80 constants are there. 80 constants. So how we generate these 80 constants? 80 constants are generated by using first 80 prime numbers. First 80 prime numbers we use, starting from 2, 3 up to 80th prime number, 80 prime numbers. Okay, so how we can write those values? K naught is obtained by taking cube root of 2. You will have some decimal representation for that. Write that decimal representation of the fractional part or decimal part into binary form, that what we discussed for initial vector, same like that only, but this is cube root for every prime number. So binary form, after writing that into binary form, you have to take only how many bits? 64 bits. 64 bits of first 64 bits and represent them in hexadecimal form and assign that value to k naught. For K1, what we have to take? Cube root of 3, and we need to perform the same. So that what we discussed for initial vector, same like that for these additive case or additive constants like that, like round constants. Okay. So what will be the output here? That HI, how you are getting that HI? Output here in this figure, HI, we are getting by performing addition modulo 64 operation. We are writing like sum of 64 like that. So which is taking previous block hash code as one input, HI minus one, and the output of this last round, which is stored in the buffers from A, B, C, D up to H for this ith round only, na? So those buffers, all these are nothing but buffers. So this is the output of this. Okay. So now we observe how that single round operation will be performed. Single round operation in Sha-512 algorithm. In Sha-512 algorithm, how that single round will be processed, or what is the operation that we can perform here, how the operations will be. See that for round 0, you are taking initial vector, which contains 8 buffers. 8 buffers. You know, buffers we are representing like A, B, C, D, E, F, Z, H. Okay. So after performing any round, again, the result of that round is stored in buffers only. So again, how many buffers we need? 8 buffers. So A, B, C, D, E, F, Z, H, like this. Now here you observe carefully how I am writing. So this one, B. So it is like output of round, any round, and this is input of any round. So in this output, this B, I'm taking like output and input. So output buffers, buffer B in the output. So these buffers are output buffers, these are input buffers for any round. So output buffer, that is this B. Okay. So for this, what we will take? We take directly the data that what we have in that buffer A. See this, what I am doing. So B, we assigned with the data. So A contains 64 bits. Na? Those 64 bits will be copied into B. Next, C. Here, I'm not discussing first for this A. So first I started with this B, so which is assigned with the bits in A. Then the 64 bits that we have in this B, that is actually in hexadecimal form, will be assigned to C. Next, the buffer C data of that input will be assigned for buffer D of that output. So D is assigned with C data. Okay. Then what about this E? E is obtained by taking some D, D will undergo for addition modulo operation along with some value that is T1. How we will get this T1? So for getting the T1, so observe here what we are doing. So the last buffer for the input, that is H. So that will be given as input for the addition modulo 2 power 64 operation. So that is one input. For this operation, another input is we are taking here some conditional function. Conditional function, it may be CH or CF. So for this function, the inputs are E, F, G buffer data. So this conditional function output will be given as another operand for this addition modulo 2 power 64 operation. The output of this is again will be undergo for addition modulo 2 power 64 operation. But for this now another operand is some rotation operation here, which is applied on this E. This one is another input for this. Okay. Then the output of this addition modulo 64 will be given as input for one more time addition modulo 64 with another input is Wi. Okay. So then it will be given as input for one more time for addition modulo operation. So for this, another input is Ki. That is, the first one is Wi, which is Q word. The second one is Ki, that is addition modulo constant or additive constants or round constant like that you can take. Okay. Then the output of this, after performing these operations, that what you are getting, that is nothing but T1. Output of this is nothing but T1. Okay. So to get this E, what we will take? D, addition modulo operation, and we take that addition modulo operation along with this T1. So here, this is nothing but D plus T1. What is this E? E is the output of that round, corresponding round. So E is nothing but D addition modulo operation with T1. Okay. So here, what is T1? T1, you observe carefully here. So T1 is starting from H. On this H, we are performing addition to modulo 64 operation with conditional function. It is CH like that, or CF, CH on E, F, G buffers, E, F, G buffers, and again we are performing that output once again is given as input for addition modulo operation. For this, another operand is that rotation operation for E bits, then another operation with Wi, that is another operand here, and another operand here, that is Ki. This one is giving T1. Okay, D plus this T1 is giving E. Now you observe what is this F. F is directly assigned with the bits that we have in E. Okay, F contains the data of that buffer E. See here. This is nothing but only E. Next for G. For G, we have to take the data that we have in F. Okay. For H, we have to take the data that we have in Z. This is G. So here G is nothing but the input of that round function. Then H is taking the input of that buffer for the round, the data that we have in Z. Then one more buffer is left here, that is A. How it is initialized here, or the output A buffer, how we will take. So this is given by, first on this A, you perform some rotation function. So rotation, okay. So this will be given as input for one addition modulo 2 power 64 operation. The another operand for this is one operand, Then second operand is nothing but majority function, which takes buffer A, buffer B, buffer C as inputs for that. That output of the majority function is one operand for this addition modulo 2 power 64 operation. So the output of this will be given, again you observe here, addition modulo operation. So these two here are producing T2. So this T2 is given as input for addition modulo 2 power 64 operation. Another operand for that is nothing but T1. This is T1 actually. So this is another operand, T1. Okay. So the output of this will be given for A. So A is assigned with T1 addition modulo 2 power 64 T2. So what is that T2 here? T2 is obtained by taking rotation on the buffer A bits addition modulo function, majority function with buffers A, B, C. So this is single round operation of that Sha-512 algorithm. Okay, so now here we will observe what is that majority function, majority of A comma B comma C. We are taking now what it returns. It returns majority. In the name itself we are having. Actually, it is defined as A and B XOR B and C XOR with C and A. But actually, it returns true if the majority of the arguments are true. So this function returns true when the majority of the arguments are true. Majority of the arguments are true. Okay. Same like this, we are having one more function, that is conditional function, which is taking E, F, and G as inputs. So how this is defined? This is defined as E and F XOR with not E and Z. Okay, not E and Z. This is actually conditional function. Okay, so these are actually bitwise operators we are using. So then you are having these rotation functions. So like sigma A, how it is defined? It is defined as circular rotation towards right by 28 bits of the operand x. This is 28 plus rotate right circularly. How many bits now? 34 bits, that operand x. But here, what is the operand? A. So in place of x, you take directly this A. Then this is actually plus. Okay. Means addition modulo operation generally we take. Then rotate right 39 bits. Sorry, this is A, A, A. A only we have to take like this. That is okay. Hmm? So what is this? ROTR power n of x represents. So this is circular rotation. Circular rotation of the bits of the argument x by n bits. Circular rotation. This is R, one more R is there towards the right circular rotation. Okay. Same like this, we have one more function, that is sigma E. That is nothing but it is given by circular rotate right of the operand E by 14 bits plus rotate right, that is circular rotation 18 bits of the operand E plus circular rotation towards right of the operand E by 41 bits. 41 bits. The 10 value is 41 here. Okay. So these are the functions that we are using in a single round, and these are the summation functions that we are using. Okay. Then after this, finally, what we have, keyword generation. Keyword generation. So how these keywords are generated? Keyword generation. So these are from the main message only. So message in the sense block. So from the block, we are generating these 80 keywords. Okay. What is the block size? 1024 bits. 1024 bits. Okay. And you know, each word is of 64 bits. So from this block, how many words we will get totally? So W naught, W1, W2, like this, we will get maximum W15. W naught to W15 means totally we will get 16 words only. Then 16 into 64, you will get 1024 bits. So 16 words. It can generate 16 words. To write W16, W17 up to W79, we are having one formula to generate the W16, W17, all these words from these 16 words that are generated from the plain text. That formula here I am giving, that is nothing but WT. T value may be 16, 17, like that. That is obtained from the previously generated keywords. It is taken by, again, this is also rotation function only by 512 bits on WT minus 2 plus WT minus 7 plus sigma 2. It is rotation. Actually, it is representing 512 algorithm like that. WT minus 15 plus WT minus 16 like this. Okay. So for example, if you take T value 16, that is W16, I want to write. So then T is equal to 16. If you substitute, then it is sigma 1 of W16 minus 2, 14, plus W16 minus 7, 9, W9, plus sigma 0, this is not 2, this is sigma 0, 512 of W16 minus 15, that is 1, plus W16 minus 16, W0. So in this, what are the previously generated words you are using? W0, W1, W9, W14. But here, unknown thing is, what is that rotation? Okay, so you observe, same like that previous case, here we are having sigma 0 on some operand x. So this is again rotation function, rotate right, that is circular rotation, the bits in this operand x by 1 bit position, XOR with rotate circular rotation towards right by how many bit positions? Now it is 8-bit positions, 8-bit positions. Of the operand x. Next, this is simply shifting right only, shift right by 7-bit positions of the operand x. Then sigma 1 power 512 of x. So it is also performing rotation operations only, circular rotation of this operand x by 19-bit positions, XOR with circular rotation towards right of the operand x by 61 bits, then finally shift right. Okay, so that is by 6 bits of the operand x. Okay, in this way we can write any word up to 79 words. So first 16 are generated directly from the plain text block, which is of size 124 bits, and these generated words we use to write the next words, that is W16 to W79, with the help of this formula. Okay, the help of this formula. So in this way we can generate hash code by using secure hash algorithm, which is SHA-512 algorithm. Okay, so what are the different applications of this SHA-512 algorithm? Mainly, this SHA-512 algorithm is used in generating cryptographic protocols like SSL mainly. This is one application. Then in nowadays, blockchain technologies and cryptocurrencies. So for maintaining that data integrity and security. So this is also used in blockchain technologies and cryptocurrencies. Cryptocurrency. Why we use this here? For generating, sorry, to provide integrity of the data and authentication. So anyway, you know that hash code is mainly for maintaining the authenticity and integrity of the data. Okay, next, password hashing mainly. Password hashing. Password hashing. So after having that password in the databases, instead of storing the password directly, hashed passwords will be stored. Hashed passwords will be stored rather than directly password. Hashed passwords we will store to maintain the security. And main advantage, these are used to generate digital signatures. Digital signatures. Okay, these are some applications of this one, SHA-512 algorithm. Okay, so thank you, students. I'm stopping this lecture for this SHA-512 algorithm, which is very, very important algorithm for your exams.